So I welcome you all in this course of Introduction to Heat Transfer, a practical oriented approach. So today we are going to see a Stefan-Boltzmann law, and in the today's lecture number 11. So before that we have seen that what are the types or the modes of the heat transfer is there, and governing equation for conduction, convection we have seen that. But right now the Stefan-Boltzmann law is a governing equation for radiation heat transfer. Once again I will repeat it. So we have seen the three modes of heat transfer. First is a conduction, second is a convection, and third is a radiation. For conduction type of heat transfer, we have seen that governing equation as a Fourier law. For convection type of a heat transfer, we have seen that governing equation is Newton's law of cooling, and for radiation heat transfer the governing equation is Stefan-Boltzmann law. So let's start this today's lecture. I am Amraraj Sawant, assistant professor from Department of Mechanical Engineering. Introduction, we are going to see the radiation heat transfer energy, or the radiation transfer the energy through the electromagnetic waves. Likewise, I have said in lecture number 10, for radiation we have seen that emissivity and the black body terms. So there where I have explained that the radiation is a type of heat transfer caused by the electromagnetic waves, and how it is done or how it is transferred, because in electromagnetic waves the charge in the atoms or the molecule will oscillate, and that oscillation will have a speed of like a speed of light. Okay, so that's why the heat transfer in the form of radiation will transfer in quickly. That's why we have get we get a sun energy on the earth surface, okay, just within some seconds. Okay, so the radiation heat transfer energy through the electromagnetic waves, and how it is by the oscillation of the charge on the atoms and the molecules. So it can occur in a vacuum. The Stefan-Boltzmann law relates the energy emission to the temperature. So this governing equation of radiation heat transfer, the Stefan-Boltzmann law, relates how much energy is going to emit according to the temperature. According to the temperature of the object, it is how much energy in the form of radiation heat transfer it is going to emit, that we are going to see with this Stefan-Boltzmann law. So historical background for the Stefan-Boltzmann law, we are going to see this. So Joseph Stefan in 1879 discovered law empirically, means he didn't experimented this law, but empirically he proved, or with some experimentation he proved that the radiation heat transfer is somewhat directly proportional to the fourth power of surface temperature of any object. So after that Ludwig Boltzmann derived this law theoretically. So after doing experimentation empirically, so this law is formed by Joseph Stefan in 1879, and after this some Boltzmann scientists derived this law theoretically and proved that this law is applicable for radiation heat transfer, and for radiation heat transfer the how much heat will going to radiate is directly proportional to the fourth power of the surface temperature of that radiated object. So this law is linked to the thermodynamics and electromagnetic theory. So this law is basically linked between thermodynamics, that is a temperature difference or temperature parameter, and electromagnetic theory. So the electromagnetic theory, why it is used here, because in radiation the main prominent factor to have radiation heat transfer is through electromagnetic waves. So the definition of this law we will going to see here. The total energy radiated from any object per unit surface area of a black body per unit time is proportional to the fourth power of its absolute temperature. So this is a typical engineering definition of this law, but what is mean to say here, that the total energy radiated by the mode of heat transfer, which is radiation, so it's radiated means its total energy per unit surface area of any object or a black body per unit time is proportional to the fourth power of absolute temperature of that object. Likewise, before I have said that the radiated energy or how much heat will be transferred with the radiation effect or radiation mode of heat transfer, that is directly proportional to the fourth power of absolute temperature of any object. So let's take an example here. Once again, this is our metal plate. If this metal plate, let's say, radiate some kind of let's say 10 watt energy as in the form of heat to the surrounding, so this 10 watt of energy is directly proportional to fourth power of surface temperature of this object. That is what the law is or this definition says here. So mathematically, this expression of for this law is Q is equal to sigma T raised to 4, where Q is a heat flux. Likewise, before we have seen this Q, which is heat flux in conduction, where in conduction we used Fourier law. So heat flux means heat Q per unit area. So that's why you can see here its unit is watt per meter square. Okay, so T is absolute temperature in Kelvin. You must remember that in radiation we are going to measure the temperature, or the temperature must be in Kelvin to satisfy this equation or to satisfy the law. And sigma is nothing but Stefan-Boltzmann constant, and which is 5.67 into 10 raised to minus 8 watt per meter square multiplied by Kelvin raised to 4. And why here Kelvin raised to 4 term came? Because it's having a fourth power of absolute temperature. So what is the physical meaning of this law? So the radiated energy increase rapidly with temperature. What is the significance or what is the meaning by this statement? Radiated energy increases rapidly with temperature. Likewise, just before we have seen this expression. So in this expression you can see here this Q is a radiated energy, means Q is a total heat transfer by the mode of heat transfer, which is radiation. So the Q is a total amount of heat transfer or the energy transfer by the mode of radiation, and this is nothing but Stefan-Boltzmann constant sigma, and this is nothing but absolute temperature. So if we increase this temperature, let's say from 100 to 150 degree, okay, so in Kelvin, just conversion of degree Celsius to Kelvin, as you know that from for converting degree Celsius to Kelvin, we must have to add plus 273. Okay, then you can convert the degree Celsius to Kelvin. So but obviously the difference will be the same. Okay, and if we increase this temperature, then because of it is having the fourth power, okay, fourth power, let's say X will be the temperature, then the total heat energy radiated will be increased by this fourth power. So small temperature change or small temperature increase will cause larger or higher energy transfer in the form of radiation. That is here physically, in physical meaning, that is here stated as the radiated energy increases rapidly with temperature. Okay, so doubling the temperature increases Q by 16 times. Here just a comparison is given. If we double the temperature, okay, so let's take again this metal plate as an example. In the first case, this temperature of this metal plate you can say consider as 100 Kelvin, okay, and in second case, this one is a metal bar having temperature of 200 Kelvin. So what is the amount of heat transfer we will get from this in a radiation heat transfer is here 100 Kelvin and here 200 Kelvin. So 100 Kelvin raised to 4 and 200 Kelvin raised to 4. So that's why if we double the temperature, the total energy radiated will get 16th time. Okay, so that's why the drastic change we can observe here in the case of total heat energy that is radiated, okay, or that is going to be transferred in the form of radiation. So this is a non-linear relationship is important in all thermal processes involving high temperatures. So as we have seen in a conduction, the temperature gradient is a linear gradient which is having downward slope, okay, in general downward slope, but if we reverse the condition, we can have upward slope, and for constant slope there should be the uniform heat transfer. But here in radiation energy or radiation heat transfer, this form of radiation total heat transfer is non-linear or exponential. That's why if we increase the T by 2 times, then we can get Q, means total heat energy radiated, up to 16th times. Okay, so black body, the ideal radiator, as before in I think so last lecture we have seen that what is mean by black body. Black body means the body which can absorb all radiation and which can emit all radiation. So black body has an emissivity equal to 1, okay, and its emissive power is maximum in overall objects, but it is not a real object. So black body is a perfect absorber and emitter of radiation, and its emissivity, what does it mean by emissivity? Emissivity is equal to emissive power of any object upon emissive power of black body, and for black body itself this will become emissivity of black body, because the object which is here is black body, and upon emissivity of black body. That's why emissivity of black body equal to, mathematically here we can see that mathematically emissivity of black body equal to 1. So examples of this radiation, that is sun, furnace interiors and human skin. Human skin is approximately having emissivity around 1. So that's why we can say that human skin will act as a black body. I think so approximately acts as a black body. Okay, so emissivity of real surfaces, as we go through that concept, gray surfaces, because in actual practice or in real world the black body is an ideal concept. Okay, we are using the concept of black body because of to solve the or to analyze the radiation problems effectively or in a simple way. So here in emissivity for real surfaces, we consider a gray body in which the wavelengths or any wavelengths can capture, and the material which is having the we can say we nominated as gray body having emissivity all over the same or constant emissivity for any wavelengths. Okay, so emissivity of real surfaces having emissivity less than 1. Why? Because ideally a black body having emissivity equal to 1, and every object or surfaces which is having emissivity less than 1, because the black body which is having emissivity equal to 1 and which is a imaginary object. Okay, but in reality the real surfaces having emissivity less than 1. So emissive power, as the Stefan-Boltzmann law suggests, the emissive power or the heat to be transferred with the emission of radiation in the form of heat transfer, or heat transfer in the form of radiation, is Q is equal to emissivity into sigma into T raised to 4, where sigma is Stefan-Boltzmann constant and epsilon is emissivity and T is absolute temperature of that surface. So for polished material, low emissivity we can observe. So that's why the polished metals are good reflectors. They are not good emitters or absorber of heat in the form of radiation. So black paint which is having higher emissivity, approximately it's 0.9 or 0.98, and so that's why the black paint will approximately acts as a black body. So the black paint can absorb the radiation and emit the radiation in maximum possible or in maximum power. So understanding this exponential nature of temperature, okay, and why it is necessary? Because if we increase a temperature, we just seen in before slides, if we just double the temperature or if we increase the temperature, we can get higher amount or in a quantity, higher quantity of heat transfer with the radiation. So the fourth power dependence of radiation on the temperature is a crucial insight. And why it is so? Because as the temperature increases, the emitted energy increases extremely rapidly. So here when the Stefan-Boltzmann law suggested that Q is equal to delta into T raised to 4, okay, so that T raised to 4th power, if we increase the temperature, then we can get total heat energy transferred by the radiation in a tremendous or rapid way, okay. So that is why the hot object like furnaces or star emit visible light, okay, and that light can be transferred within a second or the speed with the speed of light, and while the cooler object emitted infrared waves. So here you can see the example, okay, if any metal surface, okay, which is having 300 Kelvin, okay, surface temperature or absolute temperature, then it can emit heat energy. Here sigma is a Stefan-Boltzmann constant, so that's why we are not taking this value here. Likewise 5.67 into 10 raised to minus 8, okay. So directly if we calculate, because here we are just seeing that how the temperature difference will create a tremendous change in the heat transfer in the case of radiation. So here if we consider this surface temperature as 300 Kelvin, then its total energy radiated through the radiation effect, so our total energy or total heat transfer through the radiation will be 459 watt per meter square Q. So the total energy which is due to the heat transfer due to the radiation is 459. But if we double the temperature like 600 Kelvin for same metal surface, then we can observe that our total heat transfer in the case of radiation is something like 16 times before, okay. So 7350, that means 16 times the heat transfer we can get. So that is the crucial insight, or here the temperature will rapid in extremely higher way. So what are the applications of this Stefan-Boltzmann law or the radiation heat transfer in general use or in engineering application we are going to see? So infrared thermometry, as in last lecture I have given an example of thermal camera or thermal imaging which is used in some combat events. So that infrared thermometry which captures the thermal radiations okay, and that captured thermal radiation we can have image form, and that's why identifying the objects and the human body is getting some simple thing with a infrared thermometry. So next application is a furnace design and astrophysics, star and planets. So how the star and planets moves, or their actual working of star and planets, how they moves or how they create. So that is also evaluated, or that is also just we can say that analyzed by the use of this radiation heat energy. So climate science, this is one of the main branch or some exclusive thing that the radiation heat energy will have a main effect on the climate. And why it is so? If you think that our earth, okay, in earth the major of heat energy came from sun, you know that, okay, but due to which equator and the poles having the some difference in a temperature because of the geometry of our earth, and because of this difference in a temperature, the air near the equator and the pole are having different properties. Likewise, you can say that on equator the air which is having lower density, but on the pole the air which is having higher density, and because of these density differences the climate is changing. And that's why the wind which is called as trader winds, okay, that flow from equator to poles or from poles to equator with some distance, and that's why the climate for every tropical region and Antarctic region is there, and it has some meaning. Because of this radiation heat transfer, the climate changes we can observe or we can analyze in how much percent the climate is changing with respect to some earlier years. Okay, so electronic cooling, as this example is illustrated in last lecture, you know that how the heat radiation energy is important in electronic cooling for your CPUs and motherboards of laptop and PCs. So what are the limitations of this Stefan-Boltzmann law, or the heat energy which is radiated? Okay, it is only used for black bodies. Okay, for real surfaces the emissivity needs to be adjustment. That's why here we consider in actual practice a gray body, where the emissivity which is epsilon, which is emissive power of that object with respect to emissive power of black body, is considered, where in gray body the emissivity is constant overall for any type of or any kind of wavelength. Okay, so it is valid for total radiation. It doesn't show a spectral wavelength specific details. That means what? If for this Stefan-Boltzmann law is valid for total radiation, not for some specific wavelength radiation. And for doing analysis for specific wavelength radiation, there are some other methods, and that are complicated, and I think so it is covered under under your post graduation course. So requires temperature in Kelvin. This is a must condition in Stefan-Boltzmann law. You have to convert the temperature from degree Celsius to Kelvin. So it can't be applied for non-thermal radiation like laser. This is one of the exception. So it is not applied for non-thermal radiation if there is no temperature difference. Likewise, in first lecture I have said that heat transfer is only possible when there is a temperature difference. So if there is no temperature difference, okay, or if any object, let's say this metal plate, if there is no temperature, okay, then it can't emit energy in the form of heat as radiation is concerned. The first basic thing is that any object above 0 Kelvin can emit the radiation energy in the form of heat. Okay, so that's why this law is can't be applied for non-thermal radiation like lasers. It is applied only for thermal radiation only. Okay, so summary, basically this law is applied for radiation, or the radiation is governed by this law, Stefan-Boltzmann law, which is having equation, or mathematically Q is equal to sigma into T raised to 4, where Q is a total heat transfer by the radiation heat transfer, and sigma is a Stefan-Boltzmann constant, and T is the absolute temperature of that object. So radiation can occur in a vacuum, and Stefan-Boltzmann law, the total energy in the form of heat, which is radiation, is directly proportional to the absolute fourth power of that absolute temperature, and it is critical for engineering and science applications. Why it is so? Because as you know that, and as in before lecture I have taught you that in actual practices, any object or any metal body having heat transfer in the form like conduction, convection and radiation all together simultaneously. And because in radiation, if the temperature we increase, just before we seen the thing that if we double the temperature, then the total heat energy which is radiated is somewhat 16th time before that. So that's why the radiation phenomena of heat transfer in engineering is a critical parameter to design the things. To if in spacecraft this radiation heat transfer, if we going to analyze this thing, then we have to analyze in proper way, because if some certain change in a temperature will cause higher heat transfer, that's why we have to calculate or analyze as per the requirement. And that's why the heat shields which is used in a spacecraft engineering must be a critical thing, and it must be analyzed thoroughly, because only the temperature difference, a small temperature difference, will cause higher heat transfer in the form of radiation. So thank you very much for this lecture. So I conclude this lecture here. You will have 20 multiple choice question MCQ and assignment over this lecture, and you can find this in the online link which is given in a discussion forum box. So please feel free to ask me anything regarding this lecture in a discussion forum. So thank you very much.